Okay, so next up we have question 11. So a cylinder fits exactly into a right circular cone so that the base of the cone and one end of the cylinder are on the same plane as shown in the diagram below. The height of the cone is 5 centimeters and the radius of the cone is 2 centimeters. The radius of the cylinder is r centimeters and the height of the cylinder is h centimeters. For the cylinder inscribed in the cone as shown above, find h in terms of r. So to do this problem, what we're going to do is we're going to set up a similar triangles image and work off that. So if I draw sort of a triangular cross section of the cone, we've got something like this. We've got 5 centimeters here and 2 centimeters here. And into that I'm going to draw our cylinder, which is sort of a square on that cross section. What I'm going to do is I'm going to call this 2 minus r, because this bit in here is r, and this height is going to be h. So the similar triangle that we can set up is going to be, so we could do 5 to 2 is in a ratio with h and 2 minus r. So again, we've got to look at where the similar angle is. So we're talking about, if I just put it in black, if I put it in black, we're talking about this angle here and this angle here as being the same magnitude. So we have to look at this 2 minus r, not just r. So all we've done is we've taken the ratio between the 5 and the 2 and the h and the 2 minus r. So therefore, if we clean it up, we have h equals 5 times 2 minus r divided by 2, which equals 10 minus 5r on 2. And that's the answer to part A. So for B, we're going to use our h equals 10 minus 5r divided by 2. And we're going to use that to get the total surface area that's given by this equation in terms of h and r, purely in terms of r. So from here on in, all we're doing is substituting. So we had s equals 2 pi r, and wherever we have h, we're now going to insert this. So we're going to put in 10 minus 5r divided by 2 plus 2 pi r squared. So as you can see, the 2 there and the 2 there will cancel, and we'll be left with pi, oops, go back to black, we're going to be left with pi r outside of 10 minus 5r plus 2 pi r squared. So expanding out, we get 10 pi r minus 5 pi r squared plus 2 pi r squared. The last two terms are alike, so we're left with s equals 10 pi r minus 3 pi r squared. So that's our equation for s in terms of r. So then we're going to use this result to find the value of r for which s is a maximum. So we're going to recall that s was equal to 10 pi r minus 3 pi r squared. So that's s. And to find a maximum, we're probably going to have to use our differentiation. So we're going to look at ds, dr. So we're going to be left with 10 pi minus 6 pi r. So that's just using our power at the front, 1 off the power. And we've now got ds dr, or the derivative of the function s. So for a maximum, we're probably going to look for ds dr to equal 0. So that implies we want 10 pi minus 6 pi r to equal 0. So therefore we'd have 6 pi r equaling 10 pi. So just by adding on 6 pi r to both sides. And then we divide both the 6 pi, divide by 6 pi, and we're just left with r equals 10 on 6. So the pi's will cancel, and then going a little bit further, we could call that r equals 5 on 3 to get the simplest fraction we possibly can. So that's the value for which r is a maximum. That's worth 2 points, so I don't think we need to go into too much detail. From this equation here, we should be able to see that it will indeed be a maximum, because this is a quadratic, so we're going to have some sort of concave down parabola, and that stationary point there maps with the top of that parabola turning point at r equals 5 on 3. So that's the answer to this question.